Thank you. Hello, everyone. I'm Zhang from the Key Laboratory of Speech, Acoustic, and Content Understanding in China. Today, it's my pleasure to give the presentation of the IOA systems for CHiME 6 challenge on behalf of my team. First, have a quick look of the whole system. Our systems were designed for track 1, category A and B. It consisted of 5 key components: the single-channel speech enhancement, the multi-stage GSS for training and testing, the data augmentation part, and acoustic models, and the system fusion. For the front-end processing, we first trained speech enhancement and separation models to output masks as well as embeddings. Then we built our multi-channel enhancement system based on the GSS. In the training phase, we utilized a two-stage GSS with random microphone selection to generate enough training data. In the testing phase, we deployed three-stage GSS to achieve better performance. In the data augmentation, a small and a large dataset was built up with audios from different methods. For acoustic modeling, our models are based on the conventional ASR baseline, 3 types of neural networks, and 2 additional techniques, spec-all and multi-channel branch, were used. In the following keynotes, I'm to go through these components and present the detailed results. The single-channel speech enhancement and separation models followed the top systems in CHiME 5. The SE model was trained with TDN under densely connected progressive learning. The noisy data was simulated with noise and clean data. Actually, our clean data is directly extracted from the original far field data, so it is not clean. In fact, we conducted two-stage single-channel speech enhancement. The SS1 speaker model was trained for each speaker in each session, and we also built a SS2 session model, which optimized a multitask loss of PSM and embeddings, and used more data. These models all used TDN architectures. Here is the old GSS. The GSS baseline is plotted here with the number representing the stages. In the first stage, it generates ASR alignments, which is used by the second stage in iterations of CHiME. We found several modifications to improve its performance. First, good initialization of the CHiME could help its performance, as well as also integrated with the 24 microphones, that is to use all microphones. And next, the VAD for each frame can be reformulated as an interpolation of annotation and alignments. Also, we can use microphone selection. For example, SNR-based selection, we use the SNR-based selection to remove 4 and 5 microphones from the total 20 and 24 microphones. The points of 1, 2, 3 made up the three-stage GSS. Yes, from the baseline 2-stage to 3-stage, and from the 3-stage to 3-star stage, we used the fusion of microphone selection. We use the logical AND to filter the microphones that satisfy these two conditions. And we also use the VMF CHiME to replace the old CHiME model. for better spectral information modeling. Here is the three-stage GSS for testing. Compared with the old GSS, we use all the officially provided GSS baseline. We use all microphones, and we use good initialization, and we use the interpolation of notation and alignments. And further, in the three-stage, we use SNR-based microphone selection. The first stage, it outputs audios and generate ASR alignments. The second stage outputs masks iterated by CHiME, and we use it to generate the SNR information. And in the third stage, we use the filtered microphones to generate the final testing audios. The three-star stage GSS differed from the three-stage GSS by using VMFC CGM and the fusion of array selection methods. The embedding of the VMF was generated from the SS2 session model. The results are listed as in this table. Our acoustic model was CLTDLF. Our training data was the original wall data, left channel and right channel, and the baseline GSS. And as you can see, from the baseline to the old GSS, in the paper we use the alignment, ASR alignment. The WER dropped from 47 to 45, around 2 points. And then we use a better initialization, interpolation of alignments and annotation, use all 24 mics. All of these made up the two-stage GSS for testing and reduced around absolute 3% WER, and integrated with SNR-based channel selection, we got 42.14, and then we further improved the performance with microphone fusion at VMF CCGMM model. In summary, our front-end processing improves around 3.7 compared with the old GSS and 5.9 compared with the baseline. Okay, here is some examples of the different GSS. It is a blue, I think, the baseline GSS, and the next three-stage GSS. It is a blue, I think. The last two is more clear, are more clear than the baseline, but actually the 3 and 3-star sound similar. We also conducted a two-stage GSS for training. In the second stage, we directly used microphone selection with rudder. So we used it to generate 7-fold training data, named enhanced data here. For the data augmentation, we built a small data set and a large data set. The small data set is for small acoustic models, and the large data set is for large models. The small data set consisted of 2 parts: the warm audios, 2-fold warm audios, and 7-fold enhanced data, totally 9-fold. The large dataset extended the small set with audios filtered by speech-enhanced speech separation models, the simulated audios, and the original fast audios, so totally 22-fold. The cleanup and the threefold speed and volume perturbation was conducted for these two datasets. So in total, our small dataset was around 1,000 hours, and the large dataset was around 2,600 hours. For acoustic modeling, we used lattice-free MRI to train our models. Two tricks: the short utterance combination, and we used biphone train for chain modeling instead of triphone. Our acoustic models were derived from the three main architectures: the CNTDNF, the CNTDN BLSTM, where the BLSTM was interleaved with TDN and CNBLSTM. We used two modules. The spec-all was used for CNTDNF and CNBLSTM, and a multi-channel branch. It used 4 channels. It was inspired from the Chen 5's work. We used LPS and MSC to model the amplitude and phase information. We found that CN is more efficient than the TDM-BLSTM architecture, and also we when decoding, we use a reference array. Here is the results of the data augmentation and training tricks. The acoustic model is CNTDNF, and the front end is 3-stage GSS. The with spec-all and more data, the WER dropped from 42 to 33.8, and with these two tricks, the WER was lowered around absolute 1 point. So this is the best model for CNTDNF, and we use these settings and data to train other acoustic models. This payload lists all the acoustic models we have trained, and with different settings. Some use small datasets, that use large dataset, and some multi-channel branch was trained with partial update rules, and some was trained with full update. So as you can see that in each type of acoustic models, the multi-channel models usually outperforms the single-channel ones. The 3-stage GSS usually outperformed the 3-stage GSS. In our experiment, our best model was the CNBLSTM ResNet, which used residue connections and more convolutional layers. But unfortunately, we didn't have time to train a multi-channel version of this net. So in the competition, this is our best performance so far. For system fusion, we adopted the weighted average of posterior probability to fuse different acoustic models. 3 steps. For different types of acoustic models, we conducted average fusion. For different types of models and different types of front end, we conducted weighted fusion. So with fusion for different models, and we got 33.8 and 35.6, and then we fuse the different front end, and we got the final results of 33.6 and 35.1. With iron score, we trained a very simple iron to rescore the results, and finally we got 32.9 and 34.5. This is our sublimation results of category A and B. In our experiments, the evaluation was worse than development around 1.5%. And some messages we have learned from the computation. First, the initialization and microphone selection plays an important role in our front end. The fields of different front end can stably lower the WER. And the data augmentation is important to increase the capacity of acoustic models. In most situations, the multi-channel branch may help the performance, and the deep cells can bring a better acoustic models. We are still working on that. Okay, thank you.